All right, today we start our section on factoring, section 1.5. And so let's get started. First of all, what is factoring? So you know that you could take a number like 28 and factor that into, let's see, 2, 14, 7, and 2. But what you're doing there is you're actually breaking that number up into numbers that could be multiplied to give you this number, so 28. So this would be 2 times 2 times 7 is 28. So the process of factoring is breaking something up into factors that can be multiplied to give you that original product. Okay, so you're breaking it apart. And then factoring polynomials is the exact same thing. So let's read this up here. It's the process of finding polynomials whose product equals a given polynomial. In other words, break the polynomial apart into simpler polynomials that can be multiplied to produce the original polynomial. So you're breaking it apart into simpler polynomials that can be multiplied to produce the original polynomial. So let's take a look right here at this polynomial, which we've just been learning about polynomials. So there's one right there. And so this is that polynomial factored right here on the right. And so notice that it got broken up into two binomials, two smaller polynomials, that if you multiplied them would bring you back to this trinomial. Now, you could actually FOIL this polynomial and you would see that it would go back to this original. So I have this nice arrow up here saying factoring, moving this way from this trinomial to this product right here, that's called factoring. And if you want to go the other direction and get from here back to the original, that would be multiplication. You would FOIL those two binomials, which is what we just finished learning last week. All right, a prime polynomial is a polynomial that cannot be factored. So if the polynomial can't be broken up at all, like the number 13, like the number 13 can't be broken up at all, that number is called prime. Just like a polynomial that can't be factored, it would be called prime. And so a polynomial is not completely factored until it's written as a product of prime polynomials. So basically what that means is you need to keep factoring until you can't factor anymore. Right? So if I could factor this further, I would, but you can't. Those are both prime polynomials. So if the problem says factor completely, which it always, you always assume that that's what it wants, then you need to just keep factoring until it's a product of prime polynomials. Let's look at factoring the greatest common factor, or GCF. So what is a GCF? It's the greatest monomial that can divide evenly into each term of the polynomial. So you're looking at all of the terms and you're saying, what can I divide evenly into all three of those? What is the greatest factor that all of the terms have? And you need to always do this first when you factor polynomials. It will make the problem a lot easier. But always do this step first. So step 1, identify the GCF. So looking at these two terms, 6a squared and minus 18a squared, what would the greatest common factor be? So for the coefficients, the GCF there is 6. And then when you look at the variables, you're always going to take the variable with the lowest exponent. You can only take out whatever that lowest exponent is. So for this one, it would be the a squared. The 2 is the lowest exponent. Step 2, divide each term by the GCF. So divide by 6a squared. And then it says, write the GCF in front of the new polynomial. Okay, so after I've divided this, 6a squared divided by 6a squared is 1. Minus 18a to the 4 divided by this. Use your properties of exponents. 4 minus 2 is 2. So that's negative 3a squared. And then that step 3 was saying to write this GCF out front. So I'm going to put my a squared, my 6a squared out front. And so what you actually just did was undo distribution, right? So if I wanted to multiply these two factors back together, I would distribute that back in, distribute, and you would get back to the original guy. So anytime you ever want to check factoring, you can always just multiply the two factors back together, and you will get back to the original if you did it correctly. So there we go. Let's look at number 2. So GCF here. One note that I need to make here is that if you have a leading negative, you always want to include that as part of your GCF. You always want to factor that out. So let's make a note. Always include leading negative in GCF. Even if there is no GCF, but there's a leading negative, you need to factor out the -1. So your GCF would be -1, and you would divide the whole thing by -1, and you would write the negative in the front, outside parentheses, just like any GCF. All right, so what is our GCF here? Of course, the negative we are going to include. Now our lowest exponent on the m is this one right here, m to the 1. Our lowest exponent on the n is 2, so we can only take out n squared. So now we're going to divide everything by -mn squared. -mn squared. -mn squared. All right, dividing each of those negatives cancel, the m's cancel. 5 minus 2 is 3, n cubed. M squared, the 3 minus 1. Now you see why we did properties of exponents first. 3 minus 2 is 1, so we have an n here. Negative divided by negative becomes a plus. 10m cubed. The n squareds cancel. Okay, and then I'm going to write this GCF out front. Undistributed and -mn squared. All right, that's it. All right, on number 3, checking for a GCF with our coefficients, 14, 28, and 21. So that's going to be 7. And a lot of times your only GCF is a number, but on these problems we've got variables as well. So x cubed y squared, okay, looking for our lowest exponents on the x is going to be a 2. We've got 2's on both of those, so x squared. Our lowest exponent on the y is also a 2, y squared. So dividing each of these by 7x squared y squared. Okay, that gives me, you can go ahead and write that 7x squared y squared so you don't forget about it. That gives me 2x. The y's will cancel, y squared divided by y squared, minus 4. X squared cancel, leaving you with just a y there. Plus 3. X squareds cancel again. Y squareds also cancel this time, so no x or y left on the last term. Okay. All right. On number 4. This one is quite different. Our two terms here are this guy and this guy, right? A term is defined as the product of numbers and variables. So if you're looking, the only plus sign here is that one, other than the ones in parentheses. And so since this is a product, then this whole thing is a term, and this whole thing is a term. Okay, this first term and a second term. And so out of those two terms, we need to get a GCF. All right, out of x and 5, there's no GCF, but notice that these whole binomials right here, they match. And so that is the GCF. It is y squared plus 4. That whole term. So we are going to divide by y squared plus 4 on each of these terms. Okay, so I'm going to put the y squared plus 4 on the outside. If I divide this, that cancels and that cancels, leaving us with just x plus 5. And you'll see why we did that here in a second on the next page. All right, factoring trinomials with a leading coefficient of 1. So for a trinomial, ax squared plus bx plus c, which those are the usual coefficients that we use on just a standard trinomial. It's always a, b, and c, with a coefficient a equal to 1. So this guy's basically not there. List factors of c first. So just to remind you, because you have seen this before, the process is you are looking for two numbers that multiply to give you c and add to give you b. So numbers that multiply to give you c and add to give you b. So step 1 to doing that would be to find the factors of c, so 24. And if you can do this in your head, that is obviously totally acceptable. You don't need to make a t-chart. But 1 and 24, 2 and 12, 3 and 8, 4 and 6. So those are our factors of 24. And then step 2 says find P and Q, a pair of factors of C with a sum of B. So basically out of this list, which ones would multiply to give us C? Well, all of them. Which ones would add to give us B? Okay, so they multiply to give us 24. Here's our list of numbers that multiply to give you 24. And then they need to add to give us -10. Okay, so I'm seeing 4 and 6. If you do 2 and 10, then one has to be negative and one positive. But they need to multiply to give you a positive 24, and that right there would give you a negative 24. So we don't want to use that one. But if you use 4 and 6, they actually both need to be negative so that they will add to give you negative 10. And since they have the same sign, they're going to multiply to give you positive 24. So just be careful about the signs. If it's positive, then that means both of your numbers need to have the same sign. If that C is negative, like on the next one, then the two numbers have to have opposite signs. All right, so step 3, write the factored expression x plus p and x plus q. So we're just writing that out as x plus negative 4, which is x minus 4, and x plus negative 6, which is x minus 6. So those are our two factors. So that's how you factor a trinomial if you have a leading coefficient of 1. You may be saying, oh my gosh, on number 6, we don't have a leading coefficient of 1. That is terrible. What are we going to do? But remember, step 1 of factoring is always to take out that GCF. So since the GCF here is 4, we're going to do that first, and then it will have a leading coefficient of 1. So the GCF is 4, take out the 4, write it in the front. Oh, that is supposed to have an X there. That is my bad. That's definitely supposed to have, oops, not an X, a Y. So if you can just write that in. Okay, so 7y and then minus 8. Okay, now we're going to factor this trinomial that now has that leading coefficient of 1 right there. Okay, so we're looking for numbers that would add orange. That would add to 7 and multiply to negative 8. So that's 1 and 8, 2 and 4. That's it. That's all your factors of 8. They need to multiply to negative 8, so one of them needs to be negative. They need to add to positive 7. So for 2 and 4, that would not give you 7 in any way. But 1 and 8 would if I made the 1 negative. Negative 1 plus 8 is 7. And negative 1 times 8 is negative 8. Good. So now I'm going to write my factors. Use the variable that was used in the problem, obviously, y minus 1 from this negative 1, and then y plus 8. All right. Moving along to what's called factoring by grouping. So if you have a polynomial that has 4 or more terms, sometimes it can be factored by grouping. We will only give you ones that can be factored by grouping unless your only job is to take out the GCF. All right, so as usual, step 1 is to take out the GCF. So notice these numbers are all divisible by 2. So I'm going to take out this 2 first before we get into our grouping. That gives me 6x cubed plus 3x squared minus 7x minus 7. Oops. Minus 14x minus 7. Okay, now step 1 for factoring by grouping is you want to group the terms using parentheses. You're going to actually group the first 2 terms, so that's these 2, and then group the second 2 terms. But you want to leave a plus sign in between, so make sure there's a plus sign in between those 2 terms, but because they are still being added, right? All we did was just break them apart and add parentheses around them. Okay, so now we can move to step 2. It says factor out the GCF in each group. So from this first group, you're looking for the GCF, and that is 3x squared. So take out a 3x squared here. And for just a second, we are going to have multiple parentheses because I need to write my GCF right there, but it's not part of this 2 GCF. If you want, you could make this into a square bracket. Okay, so that leaves me with 2x plus 1. Okay, on the second one, taking out a -7, that's my GCF. Remember, if there's a leading negative, which there is right here on the -14, you want to take that out. So write the -7 out front, and then that leaves you with 2x plus 1. So this 2 is the original GCF that was taken out, and then we took out the GCF from the first group, 3x squared, and then the GCF from the second group, -7. And then we were left with these two binomials. Notice, this is the important part, that these two match. This only works if those leftovers match. And so that's what step 3 says. The terms left in each group should now match. So factor out the matching binomials. So just like on the last problem of the first page, we can factor this 2x plus 1 out of these two terms. So we've got the 2. Then we'll have the 2x plus 1 factored out. And the 3x squared minus 7, those are the, that's what's left after you factor out the 2x plus 1. So you'll have the other factor will be 3x squared minus 7. Okay, so those matching ones, those become one factor because you're factoring them out. And then the leftovers right here, those original GCFs, 3x squared and minus 7, those become the other factor. Okay, let's do another one like that. Number 8. Step 1, which says to group the first two and the last two, leaving a plus sign in between. So notice on the previous problem there was a minus sign right here, so I went ahead and smushed that into the second group. It has to go into the second group, and then I just added a plus sign in between. But on this one, since it's already a plus sign, you are good to just leave it like that. All right, GCF from each group. For the first one, that's going to be r squared. So we're going to take out an r squared here. And that leaves us with s plus 3. The second one, I have a GCF of 5. So divide by 5. Leaving you with s plus 3. Perfect. They match. We've got matching s plus 3 and s plus 3. So you're going to factor that out. If you want to literally divide by s plus 3, you can. And the other one is going to be your r squared plus 5. R squared plus 5. That's what's left over when you factor out the s plus 3. Okay, that one was actually a lot easier because you didn't have that first GCF to deal with. All right, that does it for these notes. We will continue on these tomorrow.